Hi everyone, this is Mr. Lee. In this video, we are going to go over Newton's first law, the law of equilibrium. With this introduction of the first law, I'm also going to slightly introduce the second law in the formula form, but the second law video will be coming up shortly. All right, let's begin. So the first law states a object in motion stays in motion, an object at rest stays at rest unless there's an outside force. So if I were to translate this, and this is like the translation that we'll be using in the classroom, I would be saying an object will have a constant velocity unless there's an outside force, and then if there's an outside force, it will accelerate. All right, so let's just do a couple of highlights. A object will have constant velocity. So the idea here is very powerful. So if an object has constant velocity, that means at a time of 0 seconds or a time of t seconds, right, the velocity initial has to equal to your velocity final. And this means that your acceleration overall is equal to 0 meters per second squared. And the big idea behind that is this last part here. Then it will accelerate. So this leads into Newton's second law. So this will be the formula that we'll be using for this part of the unit. F equals ma. You'll often see me write it as F equals ma with this summation symbol up there. So this means the total forces is equal to the mass times acceleration. Okay. So what this tells us is that if we have an object and this object is experiencing a force, then the object will be accelerating. Okay? But the whole idea for us with this equilibrium is that our acceleration is 0, therefore our net force is equal to 0. All right, always be looking out for the terms constant velocity. Now, when we first do our practice, all of our problems will be constant velocity situations, so you don't really have to keep an eye out for it. But in the future, when I throw different kinds of problems at you, if you see the terms constant velocity, this is so very important because that lets you know we are in an equilibrium scenario. All right. Okay, so strategy. You have to create a formula for your x and your y forces, much like when we did this for kinematics and projectile motions. You have to create a formula for the x, and you'll see me write it like this, equals max, and you'll have to create one for the y, which will look just like this. All right, so this little subscripts just tell us which axis we're thinking about. Okay, now here's the important part. Because our acceleration is 0 for both the x and the y, okay, all of our forces have to add up to 0. All right, our forces have to add up to 0 newtons there. All right, let's do a example. So we have a book and it's resting on a table. The book has a mass of 2 kilograms. So when we are solving these problems, it's always important to do a sketch and a free body diagram. So I'm just going to do 2 kilograms there. There's the dot that represents the object. And without doing any calculations, I'm just going to call this Fg. And here we have f of n. All right, now formula for the weight of the object, so the force of gravity is the weight of the object, is m times g. And if we know that m is 2 and g is just 10, we can multiply that together and we get 20 newtons, okay? And those are the units for Sir Isaac Newton. And I'm going to write the word down here. So we know it's going down because of the vector right there, but just in case, it's helpful, so either down or the negative symbol there. All right, so here's the important there. The book is just resting on the table, and if we know that the book has a constant velocity, and in this case, the constant velocity is 0, then we should automatically know what that normal force is, and here's how we can solve it. All right, so logically, we know that if this is negative 20 down, this normal force has to be 20 newtons up. And this is because the net force has to add up to 0, right? So that's the logic. But if I were to set this problem up, I would do sigma, or the total force in the y-axis, is equal to ma. So this is an important idea here. You have to start off with a physics formula, right? And in the next line down, right, I'm going to add up all of my forces. So we know that the acceleration is 0, right? Key point there. And this right here, it shows us all the forces in the y-axis. So we have f of n positive, and then we have f of g, but because it's pointing down, it's going to be negative, right? And so we have m times 0, which just gives us 0. We have f of n minus fg, and therefore f of n does in fact equal to fg. And the very last step, let's just plug it in. So f of n does in fact equal 20 20 newtons. All right, so see what happens here. So as long as you keep your signs in line, when you do the math correctly, right? So when we put the negative f of g over there, the negative goes away, and our final answer comes out to be a positive 20 newtons. All right, let's try another one. So for this one, we have a block of 5 kilograms is pushed to the right with a force of 300 newtons. The block is moving with constant velocity. So let's do a quick side sketch. So here we have a block of 5 kilograms. I'm going to put a little dot there to represent my object. I'm going to draw a free body diagram. So I know the force of gravity exists. Once again, good reminder, just write Fg equals mg every single time. Because we have a surface here, right? We know that the normal force exists. We don't know what that normal force is just yet, but we sure can figure it out. And it's being pushed to the right. I'm going to just call this F1 of 300 newtons. All right, so this is why drawing a free body diagram is so important. Because of this term here, with constant velocity, we know that all the forces in the x and the y axis, they have to independently add up to 0. And so here we can see that the vertical forces, right, these should equal to each other, and that's great, but here we have F1 that is not currently being canceled out by anything. So I'm going to put a F here, and I put a little question mark there because we don't know what that force is. Spoiler alert, we actually do, right? So when you push an object across the floor, what slows it down? And this is actually the force of friction, right? So here's a couple of things. This is a free body diagram. Now, for your FRQs, your free body diagram can only contain real forces. But when you're doing classwork, what I encourage all my students to do is I encourage them, like off on the side, to indicate the velocity is to the right. And this is because the force of friction always opposes motion. Meaning that if this object is going to the right, the force of friction goes against it. So the force of friction, therefore, is going to the left. Okay, so here we have our scenario. Let's get some math in. Let's do the net force in the y-axis is equal to ma. Yes, it's a little bit cumbersome to do that every single time, but that's how you get your FRQ points. M times 0 is equal to positive f of n minus f of g. And we know that fg is just mg, and this is all equal to 0. F of n, therefore, is equal to mg. And now we can put in our substitutions. M is 5, g is just 10. Therefore, our normal force is 50 newtons. Okay, so we can put that in there, 50 newtons. All right, now let's do the same for the x-axis. Okay, the sum of the x forces is equal to max. Because we're moving with constant velocity, we know that this is just 0. And here we have positive f1 because it's pointing to the right, minus f of f. Okay, so we have 0. F1 minus f of f, therefore f of 1 is equal to the force of friction. We know that f of 1 is equal to, was it 300? There we go. 300 newtons is equal to the force of friction. Final answer. All right, let's do another one. Okay, so here we have a scenario. We have an object of mass m is dragged across a rough floor with a rope. As shown in the image, the rope is pulling with a force of t. The object is moving with a constant velocity. All right, so for this one, I didn't give you any numerical values because I want to show you how to set this up in variable form only. So this is the image. What I'm going to do is I'm going to create a free body diagram, right? So here we have f of g is equal to mg, right? And we had the normal force. Now pay attention to what I just did right here. I actually made the normal force slightly smaller. Okay, and this is because what the rope is doing is the rope is actually pulling the object slightly off the floor. And so the normal force is a reactionary force, meaning that if you lift the object slightly off the floor won't have to push up on the object as much. And then, of course, we have this delta right here. Okay, so for a free body diagram, right, we're almost there, but I included this word rough for a reason, and that's just to let you know that anytime you see the word rough, that means that there's friction involved. So let's go over the idea, right? If the object is moving to the left, right, the force of friction must be pointing to the right. So we put the force of friction right there. Okay, so for FRQ, that is the free body diagram that you have to work with. However, so I'm going to just put a little box there as a reminder, right? So this is your free body diagram FRQ answer. However, when you're doing your work, that can only help you out so much. So what I'm going to do is I'm going to take this and I'm going to show you what I would personally do if I were trying to solve this problem. So that's my image, and off on the side, right, on the FRQ, you can write all over on the side. I would indicate the following. Say I'm going to say velocity is to the left. All right, so it's moving towards the left. And what I'm going to do here is I'm going to draw components. So let's draw this right here. This is TX, and I'm going to draw this up here. This is my TY. All right, so pay close attention. Arrowheads, okay? So vectors need arrowheads. These arrowheads indicate that this force of tension right here is pulling up and to the left. All right, so make sure you have your arrowheads there. All right, now the reason why this is important is because now we have to create our net force formula for the X and the Y. Let's do the Y one first. Now, this is a suggestion that I make. Whenever I do these problems, I always like to start at the 12 o'clock mark and just go all the way around my free body diagram and just double check that each force and force component is represented in my formulas along the y-axis and for the x. So for example, this f of n, right, is that in the y-axis? And the answer is yes. So I'm going to put that down. Positive f of n. This force of friction, that's in the x-axis. Don't need to put that there. F of g, y-axis, but it's going downwards, so negative. Tx, nope, that's the x-axis. Ty, yes, positive Ty because it's pointing upwards, and T. So T has the x and the y components, so we do not include T. And then we're back at the 12 o'clock mark. All right, and so this is all equal to MA, and because we're in equilibrium, we know that this right here is our formula. All right, now for a FRQ, what they might ask you to do is continue that and use variables that you're allowed to use. So what I'm going to do is I'm going to perform a couple of substitutions. We know that FG is MG, and this TY, look at this. This is back to the vectors, right? This trig notation. So TY is opposite of that angle. Therefore, this should be plus T sine theta is equal to 0. And this is my net force formula for the y-axis. Let's do the same for the x. All right, so for the x-axis, I'm going to do the same thing. Always start off with the base formula, and we know that all of this is adding up to 0. I'm going to start at the 12 o'clock mark, all right, and ask myself, is this the x-axis? F of n? Nope. F of f? Yes, it's pointing to the right, therefore it's positive. Fg? Nope. Y-axis. Tx? Yes. And that is negative because it's pointing to the left. Ty, nope. And T, nope. All right, and that's it. That's our formula. So we can see that f of f is equal to Tx if I move this over here because all this adds up to 0. And therefore, we can say all right, f of f is equal to T cosine of theta. Cool stuff. Okay, so that leads us to the very end. Just as a quick wrap up, when you are doing these equilibrium problems, all right, these are the points that I want to emphasize. You have to sketch out the scenario if one is not provided. Until you get used to these scenarios, right, having that sketched down really does help. Draw a free body diagram. No components for the FRQs, right? No XY components, only real forces. No velocity vectors. Velocity is not a force. Draw a free body diagram, okay, with components. And this is just for your work, right? But for the FRQs, you cannot have components whatsoever. But your work, they can. From your free body diagram with components, okay, that's where you can come up with your net force formulas. But before you do that, you need to make sure that you see in that problem the terms constant velocity or an idea that the object is moving with constant velocity. Okay, So this whole purpose of this video is for those specific situations when your acceleration is 0 meters per second per second. And lastly, solve. There are many different types of scenarios. We just went over 3 very basic ones. You'll see a lot of different ones in the future, but if you follow these steps, you are off to a good start. I'll see you next time. Bye-bye.